Hello students, I hope you're having a wonderful day. Today I would like to introduce a problem covering the conservation of momentum in two dimensions. So I'm going to read the problem, we're going to record some knowns, and then we're going to draw a picture and solve the problem. So let's go ahead and get started. I will read the problem here. A DeLorean with a mass of 1,233 kilograms is traveling north at 16.54 meters per second and collides with a Lamborghini Diablo that has a mass of 1,575 kilograms moving west at 17.43 meters per second. The two cars stick together when they collide. Now, what I want to do is just read part A and we're going to draw a picture. So part A asks us to draw a picture of the two cars before the collision, okay? So, since we're covering the law of conservation of momentum, it tells us that in a closed, isolated system, the momentum after the event, the total momentum of the system after the event is equal to the total momentum of the system before the event. So in this case, the event is the collision. And so the problem tells us that the two cars collide with each other. So let's draw a before picture. So right over here, I'll draw a before scenario. Okay, we have the DeLorean that is traveling north. So let's draw a vector arrow. Remember, velocity is a vector, so it shows both magnitude and direction. And so I'm going to say the initial velocity of the DeLorean is 16.54 meters per second, and the mass of the DeLorean is equal to 1,233 kilograms. Okay, so here we have the mass recorded for the DeLorean, here we have the velocity vector drawn, and then the magnitude is 16.54 meters per second. Okay, next let's go ahead and draw the Lamborghini Diablo's vector. So it's headed west, so it's going to be pointed in a negative x direction. Now I'm going to draw a point here that represents the collision of the two vehicles. Okay, so the mass of the Lamborghini is 1,575 kilograms. And the initial velocity of the Lamborghini, so we're headed west, here's my vector arrow headed west, 17.43 meters per second, okay? Now I'm drawing this point here to represent the collision, and so I'm just going to make a note. There we have the collision of the two vehicles. Now the problem tells us that they're going to stick together when they collide. And they are going to head in this general direction, which would be quadrant 2 or a direction of northwest, okay? So what we're going to do is calculate the momentum of both the DeLorean and the Lamborghini. And then we are going to add vectors graphically. So we're going to use the head-to-tail method and place the vectors right over here, and it's going to be the momentum vector, okay? So let's first calculate the momentum of the DeLorean. Remember that momentum is identified by lowercase p, and we know that the momentum of an object is the product of the object's mass and the object's velocity. So remember, if the object is not moving, so the velocity is 0, the object has 0 momentum. But the DeLorean is moving with a velocity of 16.54 meters per second. So mass times velocity. I'll go ahead and write down the base equation. So m sub, I'll say DeLorean, times the velocity of the DeLorean. So what we've got is the product of 1,233 kilograms and 16.54 meters per second. Let's go ahead and grab our calculator here. And we are going to get 20,393.82, and we have units of kilogram meters per second. I'm going to put a dotted box around this guy because we're going to need this value for our vector addition. Next, let's calculate the momentum of the system for the Lamborghini. Okay? So, remember that momentum is identified by lowercase p. My subscript of L represents the Lamborghini. We have mass times velocity. The mass is 1,575 kilograms. The velocity is 17.43 meters per second. And you can see that the vector is pointing west. So the product here is 27,452.25, and we have units of kilogram meters per second. And I'm going to put a dotted box right there. Okay, so remember that the law of conservation of momentum tells us that in the closed isolated system, the momentum after the event is equal to the momentum of the system before the event. Or in other words, the total momentum of the system is conserved. So what we're going to do is we are going to draw vector arrows for the momentum of the system. Okay, so here we have our initial velocity vectors. Here we have the collision. And then I'm going to draw my x momentum vector first. So this will be the momentum of the Lamborghini. And to keep this clear, I'm just going to copy this value over here. So we have 27,452.25, and I have units of kilogram meters per second. Okay? Using the head to tail method, we're going to place the tail of the second vector on the head of the first vector. So I'm going to place the tail of my second vector on the head of the first vector. So the momentum of the DeLorean is 20,393. Okay, so and I have units of kilogram meters per second. Okay? And so remember that the resultant vector always begins at the tail of the first vector and it ends at the head of the last vector. So what I'm going to do is connect these 2 points here. Here's the tail of my first vector. Here's the head of my last vector. So our resultant vector can be drawn like this. And this is going to be the final momentum of the system, okay? So I'm going to say P sub F. Now what we have here is a right triangle. So I'll put my symbol there, and in part B we're going to solve for this angle. It says, what direction do the two cars travel after the collision? Okay? So I'm going to go ahead and erase this since I've copied the two values here. So we're going to use the Pythagorean theorem. So here we're looking for the hypotenuse. That's what we're going to calculate. So we have our adjacent with respect to theta, our adjacent and our opposite side length. So we have c squared is equal to a squared plus b squared. Okay? In this situation, so we're going to apply the Pythagorean theorem to our situation here. So I have the final momentum of the system, so P sub F, and this quantity is squared, is equal to a squared. This is going to be the momentum of the Lamborghini squared plus the momentum of our DeLorean squared. Okay? Let's plug in some values. So I've got 27,452.25 kilogram meters per second squared plus 20,393.82 kilogram meters per second. And this guy is squared. So let's grab our calculator here. So we're going to get some pretty large numbers since we're squaring them. And I've got 753,626.30.1. Now, remember, when we square this value, not only are we squaring the numerical value, but we are squaring the unit value as well, okay? So, the numerical value squared, 753,626,030.1. When I square my unit value, I've got kilograms squared times meters squared per second squared, okay? So, moving on, we need to square the momentum of the DeLorean. I've got 20,393.82. This value squared. This is going to give me 415,907,894.2 kilograms squared meters squared per second squared. Okay? So let's go ahead and add these two values. All right, so we get a very large number here. 1,169,533,924, and we have units of kilograms squared, meters squared per second squared. On the left-hand side of the equal sign, we have the final momentum of the system squared. We need to eliminate our exponent here of 2. So what we're going to do is take the square root of both sides of the equal sign. So square root here, right-hand side, we're going to take square root there as well. What you do to one side, you have to do to the other. Remember the old algebra rule there. So when we take the square root of a value that's squared, our square root and our squared will cancel. That will leave us with the final momentum of the system is equal to, so this square root. Not only are we taking the square root of the numerical value, we are also taking the square root of the unit value. So let's talk about the numerical value first. We're going to get 34,198.45, and then the square root of kilograms squared times meters squared per second squared will be kilogram meter per second. So this is the final momentum of the system. So right over here we've drawn, and I should label this here, this is going to be after the collision. The two vehicles are stuck together and they're sliding in this direction. Okay, so P sub F, this is 34,198.45 kilogram meter per second. Okay, so now part B is asking us, what direction did the two cars travel after the collision? Well, what we want to do is use the base equation. Tangent theta is equal to the opposite side length divided by the adjacent side length, okay? So I've got tangent theta is equal to our opposite side length divided by our adjacent side length, and this is with respect to the angle theta here. What we're going to do is we're going to take the inverse of the function to isolate angle theta. This gives me theta is equal to arctangent the opposite side length divided by the adjacent side length. Okay, so theta is equal to arctangent, my opposite side length with respect to angle theta, this guy right here, this is going to be the momentum of the DeLorean. So 20,393.82 kilogram meters per second. We're going to divide this by the adjacent side length, and remember this is with respect to the angle theta, so our adjacent side length is right here. This is the momentum of the Lamborghini. I've got 27,452.25 units of kilogram meters per second. You can see immediately that the units of kilogram meters per second will cancel. Boom, there we go. Now, let's just do a reality check before we start slamming numbers into our calculator here, okay? So in the parentheses, our ratio is less than 1. And we know this just by looking, and we know that the numerator is less than the denominator. So our ratio is less than 1, okay? So that means that our value for theta will be less than 45 degrees, okay? So let's see what it is here. So I've got arctangent. Remember to hit the second function on your calculator. And then I've got 20,393.82 divided by 27,452.25. And this is going to give us 36.6 degrees. So the angle is 36.6 degrees. I will go ahead and label that on the diagram here. Let me erase my arrows and arrowhead there. So this is 36.6 degrees, okay? So I'm going to erase this now. All right, moving on. So part C says, at what speed do the two cars move after the collision, okay? Well, you know that momentum is the product of the total mass of the system times the velocity. So we have total momentum of the system. Our final momentum is equal to the total mass of the system times the final velocity, okay? Well, we know the total mass is just the sum of the mass of the DeLorean and the Lamborghini. The final momentum of the system, remember the two cars are stuck together and slide immediately after the collision. The final momentum, 34,198.45 kilogram meters per second. So we are looking for this guy right here, final velocity. I'm going to isolate it on one side of the equal sign by dividing both sides by total mass. This will give me the final momentum, the final velocity of the cars is going to be the final momentum divided by the total mass of the system. So in my numerator, we're going to use our calculated value for the final momentum of the system, 34,198.45. We have units of kilogram meters per second. We're going to divide this by the sum of the mass of the DeLorean and mass of the Lamborghini. So this is going to be 1,233 kilograms plus 1,575 kilograms. Okay, all right, let's grab our calculator here. So in my denominator, right here, the sum of these two values is 2,808, and our units are kilograms, okay, because we're calculating the total mass of the system, okay? So let's talk about the numerical value first. I've got 34,198.45 divided by 2,808. So final velocity is 12.178. Now let's take a look at our unit value. So in the numerator, I have here, let me erase this, okay? In the numerator, I have kilogram times meter per second, and we're dividing this by kilograms. Now, algebraically, we know that this is kilograms over 1. So whenever we divide fractions, it's like multiplying by the reciprocal of the denominator. So this is going to give me kilogram meter per second times the reciprocal of our denominator, 1 divided by kilogram. You can see immediately that the kilograms cancel, leaving us with meters per second squared. I'm sorry, meters per second. Okay? So final velocity of the system is meters per second. Now, the way the question is asked is, it asks at what speed do the two cars move after the collision. Now, I'm not a big fan of the way the book asks this because they're using the word speed, which I don't really like, because speed is it's not a vector, it's a scalar quantity, and we deal with vectors. So what I want to do, so our speed we can say is 12.178 meters per second, and that would satisfy the answer for the book. But let's be a little bit more descriptive here and talk about velocity, because that's a vector, so that answer has both magnitude and direction, okay? So if we were going to describe the velocity of the two cars that they collide and they stick together as they're sliding, we would say the final velocity is equal to 12.178 meters per second at, and we need to identify the angle. We've already calculated this. Here we go, 36.6 degrees. So our final velocity is 12.178 meters per second at 36.6 degrees. And taking a look here, we need to describe the direction. We're going to say north of west. Okay? All right, so our final answer here, the final velocity of the two cars that are stuck together just after the collision is 12.178 meters per second at 36.6 degrees, and this is north of west. Okay? Well, I hope this video has helped you today. As always, if you have any questions, just let me know. You can contact me over Canvas, you can call my office number, or you can just send me an email. So if you have any questions, I would love to help you. I hope you have a wonderful day.